right, this is our 5.4 notes. Graphical interpretation of first and second derivatives. Okay, so I want you to look at this graph here to the right, and I would like you to look at point A. Okay, A is referred to as a global minimum. And global means if you looked at the entire graph, global is the overall. Look at point B. B is referred to as a local maximum, or sometimes it's referred to as a relative maximum. C is called a local or relative minimum because it's where, and this is really important. Okay, let me go back up here to B. It says it is a turning point where the gradient, which we know is the slope, changes from positive to negative. Okay, that's going to be important. And a local minimum is a turning point where the gradient or slope changes from negative to positive. That's going to be important. D is called the global maximum because it's the highest point anywhere. So if you take a look here at this diagram, and let me point. So this point right here is not, and they use, let me kind of talk about this. So global, sometimes calculus books call it absolute instead of global. And local, sometimes the textbooks will say relative instead of local. All right, so here it says it's not an absolute or a relative maximum. So it's not relative or local because there's not a hill or a valley is what I like to think of. And it's not absolute because here's one that's higher. Okay, this one is an absolute and a relative minimum or a global and local minimum. This one's a relative or local maximum because it's a hill. Here, do you notice that's an open circle? So open circles means it's not a value on the graph, so it's a hole. And then this would be the absolute maximum, but it's not relative because it's not a hill or a valley. All right, so a function is increasing on an interval if as x values increase, the y values increase. A function is decreasing on an interval if the x value increases and the y value decreases. All right, we have something called the first derivative test. And the first derivative test says this. When you set the derivative equal to 0, those are called turning points. Those are called turning points. Sometimes they're also referred to as critical numbers. So if you hear me slip, this book calls it turning points. And in a lot of other calculus books, they're called critical numbers. So when the first derivative is positive and then changes to negative, then it's going to have a local maximum. If the first derivative changes from negative to positive, then it has a local minimum. Something I need to tell you about with the IB world is that if I had 1 to 3, we typically wrote that in interval notation like this. What IB does is they do a backwards bracket, because if this had been 1 to 3, it would have done like this, bracket 1 to 3. So they kind of just reverse it. So I'm absolutely fine if you use parentheses because I will use parentheses myself. However, on the IB exam or in our textbook, if they happen to use that notation where it's a backward bracket, I do want you to be familiar so that you're not confused. Okay? All right, so let's actually get to some work here. Example 1 says, consider the function f of x equals 4 minus 3x squared plus x cubed for the interval from -2 to 3. Part A says find and classify the nature of any turning points. So let's come back up here, and a turning point is where the first derivative is equal to 0. So let's do that. Let's set the first derivative. So that's negative 6x plus 3x squared. We're going to set it equal to 0. So I'm going to factor out a GCF. And I'm going to abbreviate turning points as TP. I get x is 0 or x is 2. Now I'm not ready to classify the nature. I need to do a little bit more work here before I'm ready for that. So here's what I do. I create a number line with the turning points on it, and then I'm going to test. Now they don't always alternate. About 90% of the time they do alternate, but they do not always alternate. So be careful. So what I'm going to do is, this is a test point for the first derivative. So watch what I'm going to do. I'm going to pick, say, positive 3. Okay, so I'm going to plug in positive 3 into this derivative. So it's negative 9 times negative 1. That's a positive output. All right, so now let's pick, say, 1. That's negative 3 times 1. That's a negative. And let's pick negative 1. So that's 3 times 3. That's a positive. Okay, so what does this tell us? So here's the deal. A function, f of x, okay, now we're talking about the function. A function, f of x, is increasing where the first derivative is positive. So I'm going to say negative infinity to 0, union 2 to infinity. A function is decreasing where its first derivative is negative. Now I'm going to go back. Now I'm ready. Once I get my test points done, then I can actually figure this out. So here's the deal. If a function is increasing, then changes to decreasing, okay, this is where the derivative's positive, then negative, there's a local maximum. So at x is 1, this is a local maximum because the first derivative changed from positive to negative right here. Then look what happened at x is 2. This was decreasing and then increasing. So then I have at x is 2 a local minimum. Now, can we find what the ordered pairs are? Sure. If I go plug in x is 0 into f of x, okay, I'm up here. If I go plug in x is 0, that's going to give me 4. And if I plug in 2 up here, that's 4 minus 3 times 2 squared plus 2 cubed, I get 0. So I can actually find the coordinates. All right, then part C says state if the points found in part A are local or global extrema. Extrema is the plural for maximum and minimums, okay, as a combination. So here's what you have to do. You have to check your endpoints. Check the endpoints of the given interval. So what I mean by that is I had negative 2 to 3. So let's go check f of negative 2 and f of 3, and you're going to compare it with the local max and the local min. So if the endpoints are higher, then it's the absolute. And if the endpoint is lower than the local min, then it's the absolute. So when I plugged in f of negative 2, I got negative 16. F of 3, I got 4. So what I want you to notice, so f of negative 2 is a global minimum, and f of 0 and f of 3 are global maximums. And it is possible because they're in the same location. All right, let's take a look at example 2. It says use the derivative to show that the graph of y equals x minus 5 over x has no turning points, and state the intervals where y is increasing or decreasing, then sketch the graph of the function. All right, well, let's go ahead. If I rewrite this, okay, I'm going to rewrite y. So x over x is 1, and 5 over x would be 5x to the negative 1. So I'm going to find the derivative. So I bring down the power. So I want to know for a critical number, or see, I just knew I would do it, a turning point. Okay, the turning point is where the first derivative is 0. So since 5 over x squared can never equal 0, there's no turning points, okay? There's no turning points. Okay, so then if there's no turning points, though, I do have, and this is where in other books, a critical number is where the first derivative is equal to 0 or undefined. So at x is 0, something is happening there. Okay, something is definitely happening. So what we have is 5 over x squared is always positive, right? Then y is increasing over its, I can spell correctly, its entire domain. Well, what's the domain for y? Well, y can't be, or excuse me, x can't be equal to 0, right, in the original function. So let's go ahead and make a quick sketch here. So I have a horizontal asymptote of y equals 1, and I have a vertical asymptote of x equals 0. So let me give you a moment to get a table going. So if I plug in 1, that would be negative 4 over 1. If I plug in 2, that would be negative 3 over 2. If I plug in 3, that's negative 2/3 or negative 0.67. And let's see. And change colors here. Whoops, I don't want that color. So 1 is negative 4. 2 is negative 1.5. And then I do know that's going to cross here at 5, 0. Then let's go on the other side. That would be what? Negative 6 over negative 1. So that's 6. That's negative 7 over negative 2. And what's that? Negative 2/3. Did I do that okay? Oh, no, I didn't. Hold on. So if I plug in negative 3, that's negative 8/3, or excuse me, positive 8/3. So here we go. So negative 1 and up 6, negative 2, 3.5. So there you have it. And what I want you to notice, if you look at this then, this is increasing, okay? But it does have a break at x is 0. Okay, it does have a break there. All right, so it says given a function f of x, the derivative f prime of x is known as the first derivative. Of f of x. Now, you can actually find the gradient, the slope of the first derivative, and it's called f double prime of x. Let me say that again, f double prime of x. And it's called the second derivative of f of x. All right, we have something called the second derivative test. Let f be a function where f prime of c is 0. So that's your turning point, okay, where you have a turning point. And the second derivative exists. Then, if you know, this is really interesting, if the second derivative is positive at that turning point, there's a relative minimum. If the second derivative is negative, then f has a relative maximum. But notice, if the first derivative and second derivative equals 0 at that turning point, then the second derivative test doesn't work, okay? So let's go ahead and just practice finding a second derivative. So in example 3, part A, let's find the first derivative. So you get 8x cubed minus 3x squared plus 6x. And then the second derivative would be 24x squared minus 6x plus 6. All right, then part B. Given f of x equals x over x squared plus 2, find the value of x for which the second derivative equals 0. All right, well, we're going to do the quotient rule. So we're going to do low d high minus high d low over low low. So that's x squared plus 2 minus 2x squared. So that's 2 minus x squared over x squared plus 2, the quantity squared. Now I'm going to find the second derivative. So again, I have to do the quotient rule. So I'm going to do low d high minus high d low. Okay, now this one's going to be tricky. So I'm going to have to do the chain rule within the quotient rule. So I'm going to bring down the power, decrease the power by 1, and take the derivative of the inside. And then low, low, I'm going to square a square, which would be to the 4th power. Okay, so wait a minute. I think I have... No, okay. So watch what I'm going to do. This is, maybe tidy it up here a minute. Okay, so I've got the negative 2x times my x squared plus 2 squared. And then I have a minus the 2 times the 2x. Okay, the 2 times the 2x. I'm going to make 4x. Then I'm going to have 2 minus x squared and x squared plus 2 over the x squared plus 2 to the 4th. All right, now we're getting into some heavy-duty algebra here, okay? So take a deep breath. You can do it. You can do it. So here's the deal. I have an x squared plus 2 here and here and here. So since I do, I can actually pull out one of the x squared plus 2's. And I'm going to end up reducing that with the denominator. So you are, in a fraction, you are allowed to reduce common factors, not terms, but common factors. So look, I can now cancel this. Sorry, let me undo that one. I just need one of those out of there. So now look, I'm going to get negative 2x cubed minus 4x minus 8x, and then notice that becomes plus 4x cubed over x squared plus 2, the quantity cubed. So that's 2x cubed minus 12x over x squared plus 2, the quantity cubed. Woo, okay, so now I want to, what was I trying to do here? Let's go back up here. It says find the value of x for which the second derivative is 0. So that's going to be where the numerator is 0. So I factor out a 2x, and I get x squared minus 6. So x is 0, or x is plus or minus square root 6. All right, that was a doozy. That was a doozy of a problem. All right, so if you need to, pause, rewind, watch it again, okay? I do need you to go through Edpuzzles, but if you want to just, kind of fast forward and watch without questions, you can go to my YouTube channel to pull them up there if you're trying to watch it a second time. Not the first time, but the second time. All right, part C. Given that f of x equals negative 16x squared minus 1 over x, find the second derivative of 1. We would say f double prime of 1. So the first thing I'm going to do is I need to put this in power rule form. So I would rewrite just f of x as negative 16x squared minus x to the negative 1. So the first derivative would be negative 32x plus x to the negative 2. Then I'm going to go straight to the second derivative. That's negative 32 minus 2x to the negative 3. Then I want to find f double prime of 1. And I get negative 34. All right, example 4. Use the second derivative test to determine the nature of the turning points on the graph of f of x equals 4 minus 3x squared plus x cubed. All right, so let's get to the second derivative. And to do the second derivative test, I need the turning point from the first derivative. So take that first derivative, which I believe we did this. We got x was 0 and x is 4. So then the second derivative test says this. Plug in f double prime of 0. F double prime of 0 is negative 6. So what that means from the second derivative test, if the second derivative is negative, then our 0, 4 is the local max. F double prime of 4, or whoops, was it 4? No, sorry, kidding, was kidding. That's a 2. F double prime of 2 is 6, so since that's positive, then 2 comma 0 is a local minimum. Okay, so let me kind of talk that through again. It's a little foggy. The second derivative test says this. Find the turning points from the first derivative. If you take those turning points and put them in the second derivative, if the second derivative is negative, you have a local maximum. If the second derivative is positive, you have a local minimum. All right, we have another definition, and it's called concavity. And concavity relates to the rate of change of a function's derivative, i.e. the second derivative. So a function f is concave up where the second where the derivative, f prime, is increasing. In other words, where f double prime is positive. Similarly, a function is concave down if f double prime is negative. A point of inflection is the location where the graph changes from concave up to concave down. All right, so let's look at example 5. It says, find all the turning points and determine their nature. So let's do that. So we're going to find the first derivative, which would be 8x cubed minus 8x. We set that equal to 0. So my turning points are x is 0, -1, and 1. I'm not quite ready to tell you about them because I got to figure it out, okay? So let's test. I personally do it in my head. If that's a little too overwhelming, write it out for sure, but I don't need to. So if I plug in 2, here's what I'm doing. I plug in 2. That's positive, positive, positive. So I say that's positive. Then let's plug in, let's say 1/2. Okay, if I plugged in 1/2, that's positive, positive, negative. So that's negative. Let's plug in -1/2. That's negative, positive, negative. So a negative times a negative is positive. And then let's test here. If I do say -2, that's negative, negative, negative. 3 negatives are negative. All right. So I'm going to do part B and then circle back to finish that one. So this is increasing. F of x is increasing from -1 to 0 and 1 to infinity. It's decreasing from -infinity to -1 union 0 to 1. So now, okay, let's see if we got this. This is tricky. The function is decreasing to increasing. Okay, the function is decreasing to increasing. Decreasing to increasing means a relative minimum. So at -1, this is a local or relative minimum. All right, now at 0, it's increasing to decreasing. Okay, increasing to decreasing. So that's a relative or local max. Then what happens at +1? Well, let's find out. I'm decreasing to increasing, so that's this one, decreasing to increasing. So that's a local minimum. And you can plug them in. Okay, plug in x is 0 into f of x to find the ordered pairs. So that would be 0, 1, -1, -1, 1, -1. All right, then part C. Find the intervals where the graph of f is concave up and concave down. So we need the second derivative. So that's 24x squared minus 8. So you're going to get x is plus or minus 1 over the square root of 3. Okay, if you need some, this is why we're doing that quadratic review, because at this point, I'm thinking you know how to do this. All right, so now you have to test point. This is the second derivative function, okay? So I'm going in here and I'm testing. So if I plugged in 0, that's a negative. If I plug in, let's say 1, that's positive. And if I plug in -1, that's positive. So this is concave up from -infinity to -1 over square root 3 union 1 over square root 3 to infinity. It's concave down in between those. Now, a point of inflection is where the graph changes concavity. So that's going to be at my plus and minus 1 over square root 3. So x is here, and then you could plug it back in, and let me just double check. my work here. Yeah. Okay, so what I did is I did this as a decimal then. I got 0.577. All right, and just because of time, I'm not going to actually sketch this, but I think I've got everything on here that I needed because this is going to be a long video. This is a pretty long one. All right, in the box, if f has a point of inflection at x equals c, and the first derivative at c is 0, the point is called a horizontal point of inflection since its gradient is parallel to the x-axis. So example 6 says find and classify any turning points and points of inflection of y equals x plus 1 times x minus 3, the quantity cubed, and justify your answers. Okay, here we go. All right, stay with me, guys. This is a tough section. So I'm going to find the derivative. So I'm going to do first times the derivative of the second plus the second times the derivative of the first. All right, now we do not want to multiply out all that stuff, okay? But watch what I can do. And again, this is going to be some fancy algebra. So I'm going to factor out the GCF. There is a GCF of x minus 3, the quantity squared. Okay, they both have at least 2 factors of the x minus 3. All right, then that's going to leave me with 3 times the x plus 1, plus I have 1 factor of the x minus 3 left. Then let's tidy that up. That's 3x plus 3 plus x minus 3. So that's x minus 3 squared times 4x. Oh, thank goodness. That worked out really nicely. Okay, so I'm going to have turning points at x is 0 or x is 3. We'll figure out what they're doing there in a moment. But let's go grab that second derivative. So I'm going to take the first times the derivative of the second plus the second times the derivative of the first. So that's 4 times x minus 3 squared plus 8x times the x minus 3. I'm going to factor out the GCF, well, at least the binomial part. That'll leave me with 4 times x minus 3 plus 8x. And I guess I could have pulled out the 4. So that's 4x minus 12 plus 8x. So that's 12x minus 12. I could pull out a 12. All right, so the second derivative is going to be 0 at x is 3 and x is 1. So watch what I'm going to do. I'm going to make a test point for my second derivative. And that's going to tell me multiple things, okay? All right, so if I plug in 3, that's a positive. If I plug in 2, that's a negative. If I plug in 0, that's a positive. So I have a point of inflection at x is 1 and x is 3. Whoops. All right, so now what I can do, I can also do the second derivative of the turning points. So if I look, the second derivative, I don't really care what the number is, but the second derivative of 0 is greater than 0. So that means 0 is a local minimum. And if I do 3, that's positive. Or wait a minute. No, it's not positive. Sorry, just caught this. No. This one equals 0. So guess what? That's a horizontal point of inflection. Cool. Yeah. Let me go over that again. I was like, wait, it's positive. No, it's actually at 3. My turning point was 0. So remember, that's what was up here. If the first derivative at the turning point is 0, and it's a point of inflection, possible point of inflection, then it's horizontal there. All right, let me see. Yeah, there we go. Okay, now we could, if we wanted to, if I plug in 0, I would get negative 27, and 3, 0 is the horizontal point of inflection. All right, then we're almost done, guys. Hang in there, hang in there. This one's a doozy. All right, so in example 7, this says, and this is really tricky, okay, this is tricky. This has been a tough lesson. It says, the following diagram shows the graph of the first derivative. Okay, so this is the first derivative. This is not f of x. Okay, so what I need you to remember, okay, so remember, where the first derivative is positive, f is increasing. Where the first derivative, oops, I didn't mean to type that. Where the first derivative is negative, f is decreasing. Where f prime equals 0, that's a turning point. Okay, that's a turning point. So this is the graph of the derivative, f prime. So it says, from the graph, indicate the x-coordinate of any points where f has turning points. So a turning point is where the derivative is 0. So that happens here, 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 and here. So the x-coordinates are -1, 0, 1, and 2. All right, well, remember, a local maximum occurs when the first derivative changes from positive to negative. So which one of these is the derivative changing from positive to negative? Well, that happens right here. Do you see the derivative is positive, then the derivative's negative? So at x is 0, that's going to be a local max. And where does that happen again? Positive to negative. So here's the derivative. It's positive to negative, so that's going to happen at 2. Then a local minimum occurs when the first derivative changes from negative to positive. So let's take a look at our graph. Do you see the graph is negative? This is the first derivative is negative to positive. Negative to positive. So that's going to be a local minimum. And then it's going to happen here as well. All right, the intervals where f is increasing and decreasing. Well, f is increasing where the first derivative is positive. So do you see the derivative is positive between -1 and 0? And then it's positive again from 1 to 2. It's decreasing from -infinity to -1. It decreases from 0 to 1, and then from 2 to infinity. All right, the intervals where f is concave up and concave down. Well, that's going to be the points of inflection is where the second derivative is 0. Okay, points of inflection are going to be where the second derivative is 0. So the derivative of the derivative would be your horizontal tangent lines. So that's going to happen here at point 618 and your point and 1.62, sorry. And then it happens down here at the 0.5. So it's going to be concave up where the first derivative changes from let me look at my where the second derivative is negative, okay? It's going to be concave, or excuse me, it's concave up when the second derivative is positive. So the second derivative is positive from negative infinity to negative 0.68. Okay, do you see it's positive here, positive, positive, and it's positive here, 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 union 0.5 to 1.62. Then it's concave down from negative 0.618 to 0.5, and then it's concave down from 1.62 to infinity. All right, so you might actually need to watch this again. This is a tough one, okay? This is a tough section.